Hello. Cool. Buenas tardes. It's really a pleasure to be back in Hacking Paris after a few years. Today I'm going to talk about PIN automatic try attack. Basically, it's about how we can brute force all the pins in a EMV cards for the banking, specifically. It's about a bad implementation or inadequate implementation that we found in a specific bank in the United States. So, who is Salvador Mendoza? I'm Director of Research and Development in Miami HQ. I have been talking about Samsung Pay, Google Pay, Wells Fargo Bank, some different issues regarding digital wallets. Also exploiting all my extra information with new technology, implementing Bluetooth technologies. I have been talking about NFC payments, about relay and replay attacks. I'm part of the Ocelot offensive security team, and I contribute to the Adafruit and Proxmark repositories, which is basically for the community regarding RFID or NFC technologies. And also, I love hardware. When I was a kid, I don't know, you hear about the Terminator movie when John Connor was brute forcing some pins to get some cash from the ATM. If you don't remember, I want to show you this small video when he basically implements a device and using a small pocket computer and start brute forcing that specific account. I have that memory in one of the corners of my mind all the time when I was researching about payment systems. And I was thinking probably one day I'll be able to do something very similar. Not only to have the money, of course it's going to be the main part, but to have that kind of smile that John Connor has in this video. So with this idea, I'm going to introduce this topic. So basically, what is the Pinata attack, or how it looks like when you're implementing this type of technologies. So we're going to have an agenda to have an introduction to a terminology that we're going to talk about, also about what is the EMV transaction flow, how it goes, for example, from the terminal to the back end of the back-end transaction of the user of the card. We're going to talk about inadequate implementations, which is basically what is the issue in this specific tag. It's not a vulnerability because they have all these policies or resources. They need to apply that specific implementation. We're going to have a demo, and we're going to have some conclusions regarding this presentation. About the terminology, we have CE for secure element. Basically, a secure element inside of a bank card is a small chip that validates the transaction implementing cryptograms. Basically, they are certificates inside of the card. When the terminal is making a transaction, this secure element is going to use this certificate to make the verification of the transaction. CVM is for cardholder verification method. Basically, what is that? Is like when you are using the terminal, you can use your PIN to verify the transaction, or you can use a signature. For example, in the United States, we use a lot of signature to the verification. The APDU basically is how the card communicates with the terminal when you insert it in the terminal. Basically, it's the protocol when they start sending commands and the card sending back the responses. Just to clarify, the APDU, it's not encrypted. That's why we can see or sniff the traffic between the card and the terminal. Also, ICC is basically integrated circuit card. Basically, is how it's presented. The PRC is pin retry counter. Basically, every card for the banking, they have this pin retry counter. What it does is like, for example, you insert the card and the terminal is going to ask you for the pin. Basically, you insert the pin, and it's not correct. It's going to be a counter that's going to decrease. Mostly, there are 5 or 3 different times that you have to put the correct pin. If you, after the three tries, you don't have the correct pin, that counter is going to be 0, and the card is going to be blocked by PIN, which basically you're not going to make transaction implementing PIN. But for example, in the United States, we can use PIN, and also we can use signature. So let's say, for example, that I block my card implementing the PIN, but I can continue using the card to make transactions using the signature. I think was another ARC, basically is the authorization response code. Basically, when the terminal is going to authorize the transaction, it sends this information to the bank, and the bank is going to respond with their IPC, which basically is the authorization for that specific transaction. What is the EMV contact payment? Basically, the contact payment is when you insert the card in the terminal. Basically, the terminal is touching the chip or the EMV chip, and it starts the communication, sending the first command to the card, and basically the card responding to that specific command. Normally, the terminal is going to send the first command, and after that, the card is going to respond. In this specific process, the terminal sends or reset the card to start this communication. What is the flow of this transaction? Basically, when you insert the card in the terminal is going to detect it. It's going to list the applications. Basically, it's going to know if the card is a Visa, MasterCard, American Express, or another type of bank. It's going to select the application. It's going to get the data. It's going to the identification process. It's going to verify the cardholder, implementing PIN or signature. It's going to find the processing restrictions, manage the risk, and finally, the transaction is going to complete. That means that the transaction can go through or is going to be declined, but the transaction has to finish in some way or another. So what is the main phases of these transactions? Basically, we have three different phases. We have the card authentication, we have the cardholder verification, and we have the transaction authorization. And the first part, on the card authentication, and the first part in the card authentication basically is when you insert it and the terminal starts listing what kind of card you're using, Visa or MasterCard. After that is when they ask you for the PIN or the signature. And finally is when he is going to authorize the transaction, sending the data to the bank, and is going to respond with the ARPC. Basically, for the protocol, we implement the ISO 7816, which is basically how they communicate to each other, implementing the application layer 7. And this protocol, specifically, we can see it in the NFC technology as well. Basically, they share the same application layer. And as I mentioned, this specific protocol, it's not encrypted. That's why we can intercept the transaction and modify it in real time. So how we design this kind of IPD commands or response from the card? So basically, we need to follow the structure, which is going to help us to understand all this process. Normally, how it looks a command from the terminal when it's sent to the card, we have this kind of structure, right? And we can split it to see how this is implemented. For example, we have the class, we have the instruction, parameter 1, parameter 2, command length, and the comment. So we can see it specifically what's data that is sending from the terminal to the card. And also it's the same thing from the card response. We got the data, and we have some status bytes. And specifically we have the data on SW1, SW2, which basically is the status of the previous command, which basically tells me if the command was executed correctly or is something wrong in the communication. We can start digging into the data to know what exactly is inside of this data. For example, in this response, we can know what is the dedicated file name, which basically is a structural protocol, what kind of language preference is in the communication, and different type of styles. We can use a decoder like emvlab.org to get the response for the card, put it in the website, and it's going to decode it for us, basically implementing TLV decoding process, which is basically tag length of value. All this process, you need to do it manually. But we were thinking how we can design something that helps us to understand this communication and simultaneously to inject data in the communication process. Or how we can extract data, doing something with it, and put it back to that communication. That's why we designed the EMV, or in this case, ELMA hardware, which is basically EMV Laboratory Middleware Assistant, to intercept the communication and start doing that kind of process. ELMA is based on SIMTrace2. SIMTrace2 is a company, designed this SIMTrace2 is a company from Germany. It's called Osmocom, which basically the first intent to do this kind of board is to intercept the communication between the SIM card from the cell phone to the cell phone, which basically was a man in the middle. So you can intercept that kind of data. So we tried to design something very different on the same methodology, but in this case to intercept data between the banking cards and the terminal to start seeing that kind of patterns. Delma is a board that implements USB-C, ESP32, which basically could be connected directly to a terminal or to a card, and you can connect it by Wi-Fi connection, or it could be connected by USB. You have different adapters, you have dual modes, and a standalone configuration, which means it could be a sniffer or it could be an emulator. Basically, we can emulate a banking card implementing this tool. This is how it looks for sniffing traffic. On one side, we have the adapter to the terminal. On the other side, we have the card inserted in the adapter. And in the middle, we have the tool, which basically we can dump the communication by USB or by ESP32, which is basically connected by wireless connection. So in this process, Delma toolset has different scenarios. It can be a sniffer. Also, it could be an emulator, and you have the ability to have the man-in-the-middle option, which you can alter the CVM order. Let's say, for example, that normally when you are making a transaction, you have a list of what kind of verification has in your own card. Let's say the first verification is going to be implementing a PIN, and after that is going to be implementing a PIN online. After that is going to be a signature. This basically is a list that is inside of your card. What about if we change the list? That could be possible implementing this tool. Also, we can control the communication, so we can change the terminal commands, but also we can change the card responses. So what happened if we sent more data to a terminal that it was expecting? It could be a crash to the terminal. So we can test different things that it was not possible to test it before because we don't have this type of tool. Also, we can implement the APDU faster, and of course, the Pinata attack, that's what we're talking about at this point. One of the coolest things about this tool is that we can relay data. Basically, the card can be in one location, and the ELMA tool could be in another location. We can send the data over internet, and we can emulate the data from that card specifically here, let's say. I have my card, let's say, in the United States. I have the ELMA connected to a server, and I can start emulating the transaction like the card was here personally, physically, but basically we're emulating, implementing this tool. Internally, we're using Virtual Smart Card. Virtual Smart Card basically is a software that uses for emulation purposes. Basically, it's like a tunnel to move the data between the card and the ELMA using internet. The idea of implementing Virtual Smart Card is because it's very easy to use it, and you can implement it not only for EMV contact transactions, but also for NFC contactless transactions. So you can implement it for different ways and different perspectives. The cool thing, or the coolest thing about this tool is that it has everything for relaying data over the internet. Let's talk a little bit about the inadequate implementations, about exactly the Pinata attack. If you remember about these phases, if we start with a card identification, I mentioned that the terminal starts reading the card, implementing, selecting the application, and knows exactly if it's going to be a Visa, MasterCard, or American Express, or any other card. After that, it's going to be the cardholder verification to know exactly how it's going to validate or verify this transaction. And finally, it's going to be the transaction authorization, where it sends the data to the backend, and the bank is going to respond with the authorization process, which could be accepting the transaction or declining the transaction. We're going to be focused on this part, the cardholder verification method, which is one of the coolest things about the transactions, well, and specifically for this Pinata attack. As I mentioned, the CVM is basically a list. You have no CVM required, which basically is a code in the transaction, a failed CVM processing, signature paper, encrypted PIN, a plain text PIN verification, basically performed by ICC, plain text PIN and signature paper, encrypted PIN by ICC, encrypted PIN by ICC, and signature paper. Let's say that you have a bank card, and you have a PIN for that card. That specific card has 2 PINs. You only remember one because it's always checking to the online transactions. But another PIN normally is saved in the card by itself. So it could be a different PIN, but normally it's the same PIN all the time. So what we can do, we're going to focus on the plain text PIN verification performed by ICC, just to learn a little bit more about the CVM verification methods. The CVM, where we can find this CVM list to understand more how it's communicating this list to the terminal. Let's focus on this card response. In the card response, we're going to focus on the 8E tag EMV, which basically tell us that this is going to be the list of the CVM verification method for this specific transaction. If we decoded this CMV tag, we can notice what is the CMV list verification method. And we decode more, break apart this verification, we can notice that this transaction specifically has the plain PIN by IC if terminal supports CVME verification method. So we're going to focus on this 4103. As I mentioned, we have this list in the transaction. And it goes, you can see it in that way. For example, the terminal is going to take the 4203 as first rule to verify the transaction. But what happened if the terminal doesn't respond to that specific rule? So it's going to jump to the next rule, in this case 4403, and after that 4103, and finally the 1F03, which basically we don't need any verification method, so you can basically authorize the transaction. So what happened if we move this list back and forth? So we are going to reduce the security of the transaction, basically. But we're not going to do that, basically, because it's going to be another tag. But we're going to be focused on the 4103. How we know that we can send a command to the card to verify a PIN that it could be basically verified by physically with the card. So we can design a command, which is stipulated in the AMV standards, that we're going to validate or verify the PIN 1, 2, 3, and 4. So we design this command, and we send it to the card. The card has different responses. Some of them, or the most important one, is 9000, which means the PIN is correct, basically. The next one is 63C2, which means it's a wrong PIN, but you have 2 more attempts left, so you can try different PINs. 63C1 is a wrong PIN, 1 more attempt left, and 63C0, which is basically wrong PIN, no more attempts left. If we arrive to this last answer for the card, means that the card is going to be blocked, and we cannot send any more attempts to another PIN. So basically, it's a mechanism to protect about brute force attacks. That's how theoretically it has to work, right? But the cool thing is if we focus on the cardholder verification part, we can start sending data to the card, and we start asking how many tries the PIN retry counter has inside of the chip. So we start sending these commands, and we start getting that you have 3 attempts left in the card to brute force a PIN. We start with the PIN 0718, and the card responds with 63C2, which means it's a wrong PIN, but we have 2 more attempts left. And we can continue sending, trying to figure out which is the correct PIN, implementing the brute force attack. And finally, we got the 63C0, which means none of the pins I tried, they are the correct, and now the card is blocked. So I cannot send more attempts to guess the PIN. So at this point, when we have the PIN retry counter equal to 0, which means the card is blocked. So how we can reset it to its previous value, which was 3 in this case, to continue sending pins to the card until we get the correct PIN? That's the main question. So there are different ways. But the most important is when you are going to, let's say that you forgot your PIN. You try different pins in the terminal, and none of them is the correct. Suddenly you remember the PIN, and you go into the ATM of that specific bank, and you insert in the ATM, and you put the correct PIN. The ATM is going to reset the PIN retry counter, because it contains the scripts to do that automatically. Another way is when you call the bank and say, you know what, I forgot my PIN, can you send me a new one? They send you a new PIN, and when you go to the ATM and use that PIN, it's going to reset that PIN retry counter. Another way is when the card has these scripts inside of the chip, and when you make a transaction, the terminal is going to communicate to the back end, with the bank, and the bank is going to send the order to reset this PIN retry counter. So we're going to take advantage of that specific resource. So basically, this happens when the banking sends the response for the authorization process, and in the authorization process, send a specific command to do that resetting the PIN retry counter. So we're going to focus on the transaction authorization process. In the last part of the transaction, the terminal sends this command. Basically, after a few logs, let's say 100 logs, different transactions, we notice that that specific bank, when it generates the cryptogram, the terminal, to make the last part of the transactions, the bank responds with this specific 0318, which basically was that byte that was changing after the PIN retry counter was equal to 0, and we're making another transaction. Which means that after that, we can start sending transactions by changing, instead of using the PIN to make transactions, we're using the signature CVM, which basically telling the terminal that we don't have the PIN, but we can make the transaction by signature, so it can go through to the bank. And the bank responds that, okay, I know that your card doesn't have any more PIN retry counts left in your counter, we're going to reset automatically, without questioning why you don't have these more attempts left in the PIN retry counter. So basically, in the last part, sending this command to the card, there are specific bytes that tells what it's going to do to reset this PIN retry counter. So to be able to do the Pinata attack, the card has to be able to use plain PIN by ICC, and the financial institution will reset the PRC when it's equal to 0 and you don't have more attempts to do it in the next transaction. And we can do that implementing another type of verification, which could be a signature transaction. So for this specific scenario, we have the ELMA setup, we have the Pinata attack. We are going to use a GPD pocket. We're going to use a card reader, SER3310, which is basically the cheapest one that you can find on the internet. We're going to have the ELMA, of course, and we are going to use the SUM app, which is basically a mobile terminal that you can have to do that. And for automation, we're going to use AutoClicker, which basically what it's going to do is after we have a 0 and a PIN retry counter, is going to try to make another transaction to reset this specific counter. So we can continue brute forcing the pins to basically continue brute forcing the pins. So this is all the setup. Basically, we have the card on one side. We have the computer, which is going to be the man in the middle. We have the ELMA, which is going to send the commands and responses between in this case, the laptop. And the laptop and the client is going to intercept the communication and changing this data automatically. And of course, we have the SUM app, which is basically connected to the bank institution to make the transactions, right? So how it looks inside. Basically, we have the card reader connected to a computer. The computer is connected to a virtual card reader, which basically is the process to intercept the communication and change in real time. And this is going to send to ELMA, and ELMA is going to emulate that data to the terminal. When the terminal sends a command back, it's going to process that command. If we have some kind of rule in the client, it's going to process that rule, and it's going to change the data if it's necessary, and it's going to send that to the virtual card reader, and that virtual card reader is going to send back to the physical card. So all this process in real time. Of course, when you run this specific script, you specify which kind of things you want to modify. So what is going to happen in demo? Basically, we have a transaction certificate, we are going to ask if we have plain PIN verification method in the card, and if the PIN try counter is greater than 0, we are going to try to brute force 3 different pins. If there is no correct PIN, we're going to have another transaction to reset that PIN retry counter until we find the correct PIN for that specific card. So we're going to be focused on the part of the reset the PRC and avoid charge. Let's say that we're making transaction to reset the PIN retry counter, but we don't want to charge, or the terminal charges for reset the PIN retry counter. Because we control the communication, the last part of the transaction is going to be a void, so they don't, the bank is not going to charge us to make these transactions. Just we need to reset. We want to reset the PIN retry counter with avoiding any kind of charge to that specific card. So let's play this video. Basically, what we have here, we have the sum up connected to the adapter, connected to a terminal, and in this case to the Elma. And we have the man in the middle client, which is we're going to run to basically start the process of this attack. So at this point, we're going to start with our clicker to start a new transaction. After this transaction, we are going to try to brute force the first 3 pins to see if we can find the correct pin. If we couldn't find the correct pin, we're going to create a new transaction to reset the pin retry counter to try 3 different more pins. So in this case, in this particular try, we couldn't find the correct pin. So the system continue making transaction to reset the pin retry counter, and it does. Basically, that's a bad implementation and an inadequate implementation. In this case, we are trying 0718, 0719, 0720. We didn't get the correct pin. And we continue making transactions without charging, of course, to try to find the correct pin. So let's see in the last try. In the last try, we're going to get the correct pin. In this case, it's 0722, which basically is the correct pin for the card. So how can I test it? So basically, I can make a transaction implementing that pin. That specific part is using the pin that we just brute force, implementing this type of pin retry counter reset methodology. Of course, we report this issue to the MasterCard environment technology company, and they send it to all the banks so they can fix or apply the policies they need to. I think we're going to have 15 minutes for the questions. I need to say a special thanks to these people that help me a lot for this research. Please, if you have any questions regarding the presentation, if you need the slides, please let me know and I can share with you. I don't know if you have any questions regarding this brute force attack.
Hi.
Yes.
Could we forge the responsive code from the bank ourselves to reset the code without a transaction to the bank?
Sorry, I can't hear you the first part.
You said that we tried 3 times, and then we make another transaction to reset the counter. Like, what's preventing us from resetting the counter ourselves?
So what it does, the system, what it does basically is when you don't have any more attempts left, we send a new transaction to the bank, but not implementing the PIN verification method, implementing the signature method. And the bank, in this case, the backend, it doesn't have, doesn't have the policy correct, let's say, and he accepts the transaction by signature. And when they accept it, they send a command to reset the PIN retry counter automatically. So that's a bad implementation. They don't have to do that. Basically, you need to call, or they need to, make an error to say, you know what, you can make this transaction. And after I test it, after they fix it or they apply these policies, my account was blocked after the first attempt. So that's something pretty cool. I don't know, you have any, I think in the middle, they have another question.
Hello, is it working in any country? Because in France, I think that once your card is blocked, you can call by signature.
You cannot?
No, only US.
Yes, but we see some issues not only in the United States, we see some issues in Europe too. Because it's not about that the terminal is not going to accept the transaction. It's if the card has that kind of technology inside of it activated. That's the main concern. Even when you, for example, in Europe, don't have that kind of technology activated, or is chip and signature, let's say, in the United States, you have chip and pin here. If the card has that kind of technology, if the policies are not applied correctly in the back end, it could be possible to do this. We noticed some issues with some companies here in Europe as well. So I don't know, you have any questions, or you're ready for the break? Yeah, thank you.